Let's talk about subspaces of Rn. So first, the definition. A subspace of Rn is any set H in Rn that has the following properties. 1. The zero vector has to be a vector in H. 2. For every pair of vectors u and v in H, the sum also has to stay in H. And 3. For every vector u in H and c scalar, the scalar multiple c times u is also in H. So this item 2, this is often called being closed under vector addition. If I take two vectors in H, then the sum has to stay in H. The third one is often called being closed under scalar multiplication. So if I take a vector in H and a scalar, then the scalar multiple also has to be in H. So, for example, let's consider H to be the span of the vector 3, 1. It contains the zero vector of R2. If I take 2 points in H and add them, take 2 points in this line and add them, they stay on the line. If I take a point in the line and scale it, it stays on the line. And so H is therefore a subspace of R2. Now let's consider this green line, K. If it fails any of the properties, it's going to fail to be a subspace, and maybe the easiest one to see is it's not a subspace because it doesn't contain the zero vector. Let's look at another example. Suppose we consider the first quadrant in R2. So H is shown here in yellow. I claim that H is not a subspace of R2. How can we see that? Well, the point 2, 2 is clearly in H, but if I scale or multiply that by -1, I get the point -2, -2, which is not in H. Right? And so therefore, this is not a subspace of R2. Let's try to see that we've seen examples of subspaces, lots of subspaces already. So here's a theorem. If I take a collection of vectors v1 up to vp in Rn, then the span of those vectors, let's call it S, is a subspace of Rn. And so how would a proof of that go? Well, it's clear that S is a subset of Rn, since each of the vectors is a vector in Rn. And now we just need to verify the three properties, the defining properties. So first, why is the zero vector in there? Well, if I take the linear combination with weights all 0, I get the zero vector. And so the zero vector is an element of S. Now suppose u and v are vectors in S. That tells me that there exist weights, a1 up to ap and b1 up to bp, such that u is a1 v1 up to ap vp, and v is b1 v1 up to bp vp. Right? U and v can be expressed as linear combinations of v1 up to vp. And now to show that the sum is an element of S, what I want to do is try to show that the sum can be expressed as a linear combination of v1 up to vp. And so let me just take the sum and compute what it is. So I can use the fact that vector addition is associative and commutative and regroup these terms using properties of vector addition and scalar multiplication. And I see that it's a linear combination of v1 up to vp. And therefore, it's an u plus v is in S. Third, now I take a vector u as above and a scalar c, and I want to show that the scalar multiple is also in S, meaning I need to show that the scalar multiple c times u is a linear combination of v1 up to vp. So I just compute c times u and use properties of scalar multiplication. In particular, it distributes over vector addition, and I can regroup. And so I see that c times u is a linear combination of v1 up to vp. And so therefore c times u is an element of S. And since I've shown properties 1, 2, and 3 that S satisfies those properties, by definition S is a subspace of Rn.